Objective 3, the factor theorem, is the third objective in the topic roots of polynomials. Up until now, I've talked through objective 1, the fundamental theorem of algebra, and then objective 2, the remainder theorem. So the factor theorem is very similar to the remainder theorem. It's just presented as a factor form instead of a root form. And specifically with this objective, by the end of it, you should be able to use synthetic division to evaluate functions and to prove that factors exist for specific functions. So, to begin, the factor theorem states that if there is no remainder, similar to the remainder theorem, or, I'm going to put up here, remainder of 0, after dividing out the function by k, the polynomial x minus k is a factor. So, the only difference between the factor theorem and remainder theorem is, if you notice again, the remainder theorem, we use synthetic division, and we're going to use synthetic division for factor theorem as well, but the remainder theorem already gives it to you in root form, right here. So if you remember, you do your synthetic division box, and the root goes right there for the divisor. Now, for the factor theorem, or if it's asking you to divide by a factor, you have to use the root form of that factor, not the factor itself. So if you notice, it says after dividing the function by k, the polynomial x minus k, or the factor x minus k, is a factor. Now, they switched it. They solved for x, they plus k. So they're using the root form, x equals k, the positive instead of x minus k. So I'm going to show you an example of what I mean, but it's the same process. If I divide this by a factor, and there's no remainder after we do this, then I know that that factor that we're dividing it by is indeed a factor of the polynomial. And going further, the root is also a root of the polynomial. So I switched it up on you. Please make note of that. I'm going to do the bottom one. On your paper it says that I'm doing the top one, but I switched it so because I want to show you this process because the bottom one's a little bit more extensive. So for the I do, it says that we know that x minus 2 and x plus 3 are factors of the polynomial m of x. It says to factor them out, then find the remaining factors. Now, this is a little bit different than what I'm going to have you do in your practice problem. So I'm going to assume that I don't know that x minus 2 and x plus 3 are factors. So I have to check to see if they're factors using the factor theorem. I'm going to synthetically divide out the root form and then see if the remainder is 0. If it is, I know that they're factors. All right? So that's the process, and that's the process I'm going to have you do on your practice work as well. So I'm just going to show you that step. Now, this leads into the next topic of actually solving polynomials and finding all the roots. And so you're going to be able to see ways to actually do that as well in this process. So I've listed out the steps in red. The first step, and this is different than the remainder theorem because the remainder theorem actually gives you the root. But the first step states that I have to change from factored form to root form. So I'm going to switch both of these factors to the root form because that's what I need to use to divide with. So x equals 2 here, and x equals negative 3. That's my first step. I've switched to the root form. Now, I synthetically divide using both of those. It does not matter which one I do first, all right? And so in this process, I can pick either one, 2 or negative 3. I'll start with the root form of 2 again. And then my next thought is, so I did step 1. My next thought for step 2 is synthetically divide the root out to check for a remainder. So I'm going to use synthetic division, so there should be a little bit of a review for you. And so I'm going to look at the coefficients right here, 2, 7, negative 4, negative 27, and negative 18. And I should also note that the powers go in descending order, 4, 3, 2, 1, and then 0. So I don't need any space holders either, so I just list out the coefficients. 2, 7, negative 4, negative 27, and negative 18. Alright, so I dropped the first number, multiply to the outside, add to the inside. 2 times 2 is 4, 7 plus 4 is 11, 2 times 11 is 22, negative 4 plus 22 is a positive 18, almost wrote negative. 2 times a positive 18 is 36. Negative 27 plus 36 is 9. And then 2 times 9 is a positive 18. At this point I draw my remainder box. and negative 18 plus positive 18 is 0. So this tells me two things. Because there's a remainder of 0, I know that the factor form, x minus 2, is a factor, and the root form, x equals 2, is a root. So the first one checks out. Good to go. Now I can check the second one, and I could do it from the beginning process, but I'm going to do it from the numbers that I have already listed. And so if you're ever going to, and again, it shows itself in the next topic where you're going to synthetically divide more than once. So the same process, the synthetically divide more than once, I use my new numbers that are listed 2, 11, 18, and 9, and I'm just going to evaluate the next root, negative 3. All right? So I drop the first number, 2, multiply the outside, add to the inside. Negative 3 times 2 is a negative 6. Add that. 11 plus a negative 6 is 5. Negative 3 times 5 is a negative 15. 18 plus negative 15 is 3. And then negative 3 times 3 is a negative 9. Draw my remainder box. 9 plus a negative 9 is 0. So because, again, the remainder is 0 when I evaluate this root, I know that its factor, x plus 3, is a factor. And I know that its root, x equals negative 3, is indeed a root. So this completes the objective. If you can synthetically divide a root out and see what the remainder is, and tell me if the remainder is 0, you know that it's a factor, and you know that the root is in a root. You've completed and mastered this objective. Now, if the remainder isn't 0, I know the opposite to be true then. It is not a factor, and the root form of that factor is not a root of the given polynomial. But both of these, 2 and negative 3, and their factor forms, are factors and roots of the given polynomial. So at this point, you are done with the objective. I just want to show you quickly what you're about to see in the next topic. So at this point, after I've synthetically divided, I need to rewrite my new numbers in polynomial form. Every time you synthetically divide, you lose a power. This was the highest power of 4. I synthetically divided twice, so my new highest power is just going to be x squared. The highest power of 2. 4 minus 2 is 2. Then I just go down the line. After x squared, it's x to the 1, and then my constant 3. So if I rewrite it in polynomial form, 2x squared plus 5x plus 3, this should look familiar to you, and this is why the process of synthetic division is so important, because now we've gotten it down to a factorable or solvable polynomial. It should look familiar. This is a quadratic trinomial. Because again, the next topic, you're going to have to find all of the solutions of polynomials. So this, you could set equal to 0 and use the quadratic formula to find the rest of the solutions. So just keep that in mind. But again, for this objective, I want you to get to right here. Synthetically dividing out, seeing what the remainder is, and then telling me if it's a factor and a root based off the remainder. So go ahead and pause the video and try the you do section of this handout. Check to see if x minus 2 is indeed a factor of the given polynomial. And then, if you can, try this. Factor the entire function completely. You should recognize the remaining pieces of what you get, and then factor it to find all the factors of the given function. So go ahead and pause it and try to see if the factor is indeed a factor of the polynomial. You should have paused the video and tried the you do problem on your own. Okay, so the first step, what I did was I switched from factored form, x minus 2, to root form. Step 1. Then I determined it was x equals 2. Then I divided by the root form, synthetically divided that out, and please check your work. Notice there's no space holders that are needed because there's no jumping of powers. So I listed out the coefficients, multiply to the outside, add to the inside. I did get a remainder of 0. So because there's a remainder of 0, the given factor is indeed a factor of the polynomial, and its root form, x equals 2, is indeed a root. So if you got to here, you are tracking with this objective, and you are ready to move on to the practice work. If you didn't get to here, please raise your hand so I can come check your work. Now, real quick, the bonus idea, if you notice here, I rewrote what was left into a polynomial form. It's x squared plus 8x plus 15. So after I synthetically divided out that root, I was left with this quadratic trinomial. This should hopefully look familiar to you, and you can factor to find the rest of the factors by using, in this case, MAC-AB. Down here I had to use the quadratic formula because the leading coefficient was greater than 1. But here the leading coefficient is not greater than 1. So I could use MAC-AB to finish this out. But again, that's just a precursor into the next topic.